All right. Well, today we'll be moving on to viscoelasticity. We'll start in on that. We certainly won't get towards the end of that today. But what I wanted to do is talk about the design values and moving from. We've been talking about properties of small clear materials and adjustment for moisture content, and here's the tables. And we said, well, lumber is different because you've got knots and cross grain, and we've talked about the effect of grain angles and being able to do tensor transformations and Hankinson's formula and all that. When a structure, when we get into talking about a structure per se, there are because of public safety, all buildings are subject to design guidelines and building code authorities. And all building code says material that you use must be certified. That's why, for example, we have grade stamps for lumber. We have a number 1 lumber, select structural, and each grade of material, there is a tabulated source that says here are the mechanical properties. So what we're going to go is talk about some of the steps in going from testing of clear material to design values that are used for structures. So this is a portion, I guess I can start this. There are tables and tables and tables of design values. This is some numbers. I've just pulled this out from what's called the National Design Specifications for a structural glue laminated hardwood timber. There are, and when they give us design values, there are 5 properties that we use, that engineers use to design a building. It's the bending strength, or we talked about modulus of rupture. This in the design community, a lot of times you'll say F sub B, where F is a allowable design value, and B stands for bending. In this case, they also give us the tensile strength, and they say it is the same. So they're assuming the tension strength and the bending strength are the same numbers. So F sub T for tension. Actually, this probably isn't the best source because these aren't the actual design values. I wonder if I can. Trying to find it real quick, but I didn't. They will give you values for compression parallel to the grain, which is called F sub C. They will give you design values for the modulus of elasticity, E. Shear parallel to the grain, and they use V for some reason. And compression perpendicular to the grain, FC perp. So there are six design values, F sub B, F sub T, F sub C, E, F sub V, and FC perp. There's no toughness value, there's no side hardness value, there's not tension perpendicular to the grain. There's just these 6 values. F sub T, F sub C, F sub B, E, FB, and FC perp. And based on, and for 98% of everything built, these are the only values that you need for to look at the material behavior. So how do these numbers get in the design guidelines that engineers use? So the first thing that they'll do is they can conduct tests. They can break stuff. So for example, and we started this off, talked about this a little bit at the beginning of the semester, because of the Norway spruce going on, testing that was going on, is you can test lumber with defects. There are standards such as D1761 where you can test the behavior of fasteners, nails, screws, because that's part of a building design process. Here's another standard for properties of lumber or wood-based. They don't say lumber, but this can work with a composite material, laminated strand lumber, laminated veneer lumber. Can also be tested under this guideline. We'll be looking at this later, and in fact, is evaluation of creep and duration of load. Creep effects on wood and wood-based products, D6815. That's another standard that is used to evaluate materials. So we'll be looking at this 6815. And there's thousands more, but I just pulled out some of them. There are some additional standards. Again, if we're looking at lumber, is standard D245 goes through all the procedures, the calculations necessary to get these design values from testing visually graded at lumber. So whether we did D4761 or D198, it's a long process, and we're not going to go through all of it. We can give you 80, 90-page reports that go through it, and that Russell's gone through, but we'll go through some of the highlights, I guess. There's also a standard for establishing the clear wood strength values. Those are the numbers that are in the wood handbook, are the clear values. And there's procedures associated with that. How do you test it? How do you analyze the data? What are the statistics that you employ for all of this? And D2915 is another standard, again, on determining these allowable values, these 6 values, FB, FT, FV, E, FC, FC perp. Again, there's a series of composite, or a series of standards. But I want to talk about specifically visually graded lumber. And so this is the equation. We can think of the procedures as this, where F is our allowable design value that we talked about that is tabulated. This is what you would look up in the code. And then we have a base value that we then multiply by a whole bunch of adjustment factors. And I'll define what all these adjustment factors are shortly. But these are all multiplications. I think I can, yeah. So here's what these adjustment factors are. So the base value, we'll define what that means later. K sub t stands for duration of load adjustment. Duration of load refers to time. So that's going to introduce us to this viscoelastic concept of viscoelasticity, creep rupture, and those kinds of things. There's what's called a safety factor. Just because. Sometimes it's called a factor of ignorance. We don't really know. We don't want things breaking. So we're going to put in some conservatism and have a safety factor. Some things it's important to be safe about. Some things aren't so important to be safe about. Special adjustment, K sub p, is used, for example, and I'll show this here later, the depth effect or the volume effect of a material. We adjust everything to a depth of 12 inches. We'll see that number. There's something that's called strength ratio, case of D. That relates to the grade of the material, knots, slope of grain. So the base value is going to be, in essence, a clear wood value. Case of G is special grading. That ties in for some grades, at least there used to be opportunities if it was very dense material. A large number of rings per inch. We'd have this case of G. And M stands for the moisture content. We saw the impact of moisture in equation form. And you'll see that come out from a tabulated value. So the strength of wood, you've got the clear values, time impacts things, safety factor, and this really ties in because not every two pieces are the same. Our results are variable. If everything was the same, then we wouldn't need it. So this really ties in with variability. This relates to a volume effect that we'll talk about. This refers to the amount of defects. This refers to density, and this refers to moisture. All of these factors impact the mechanical properties of lumber and solid wood. You'll get this. I'll share this with you. You probably don't want to copy all this. But let's go through this table. So our first column is the property, right? We had these 6 design values, F sub B, F sub T, C, C perp, F sub B, and E. Then it says, what is our correction base, or our base value? And we see 2 things. One is called the L5 and one is called the mean. So this refers, again, to our statistical variability. The mean would be, the standard says you'll test a certain number of samples. This would be our average, or our arithmetic mean. This refers to the lower 5% exclusion value. That is, 95% of the values would be above that, 5% would be below that. Duration of load, we'll talk about what that means. That's a value of 0.625 except for the E, where the value is 1. We have a variety of safety factors, and again, E, we don't have the safety factor adjustment, and FC perp, we don't. It won't break, it won't crush FC perp. It can keep crushing, but nothing's going to break, nothing's going to fall apart, so we don't need to worry about it. But these other properties are significant drops. Special adjustment, this refers to the depth. I think we'll see the equation later, but we adjust every piece in bending. We adjust everything and assume that it is a nominal depth of 12 inches. Strength ratio, this will depend on the grade. Special grading, here we see that for some species, what's called a close grain, which is only for Douglas. You can't see this. Here's the superscript 2. Douglas fir and redwood, you can get a close grain, and Doug fir and southern pine, there might be a dense grade. And if it qualifies as a dense grade, you get a 17% increase. That's less common, harder to find these days. And then we have moisture content adjustments. If it's below 15, it's below 19. Greater than 10, or if the material is more than 5 inches thick, what the adjustments are. So we'll go through all of these in more detail. Oh, this is once partially dried. All right. So I guess I just talked about the L5. So if we have let's let's assume we have a normal distribution. We test a lot of pieces. The mean value is 825. Standard deviation is 82.5. Therefore, there's a COV of 10%. The L5 value would be 689.3, which is shown right here, that location. This curve was generated using Mathematica, and then cut and paste. We can show you that later. But you could also test a material and say the mean could be the same, 825, but it's more variable. Let's just say it's twice as variable. The COV is 20%. In that case, the COV would be down here at 553.6. So the same average value, but the more variable material has a lower 5% exclusion limit. In this case, that difference would be 135.7. Should be 689.3 minus 553.6. So recall that our base value, if we go back here, the bending strength, for example, base 5, we start at that L5 value. Now it turns out that most composites, which is one of their benefits, have a lower variability compared to solid wood. And so if we had, I think I've got another deal there, I could have a composite material that on average had a lower strength by 135.7. That has the same variability. If I move that down, with that same variability, they would have the same base value of L5. So that's often, you can't be, composite materials, wood composites will not be better than a piece of wood with no knots, with straight grain. It just can't be better than that. But you just don't get that very often. So composites are less variable, but it's that L5, that base value, that's the basis of design values. So why, and so you test, you target to have a lower average strength than lumber, for example. But it turns out to be effectively the same, even though many pieces of lumber will be stronger. But in aggregate, they're going to behave. It's that low value that controls their behavior. So that's a concept for wood materials. But we have to incorporate that variability, and it's the bad actors. Think of it kind of like a chain. If you got one bad link, the whole chain fails. So it's those low values, those bad actors that control. Which is a reason that in grading, or sometimes plants can go through and regrade material. If you can pull out those couple bad pieces and retest, then everything, you can get a much higher value. In fact, that was done with this Norway spruce testing. There was some samples that were very low in properties. And said, well, why is that? The graders went back and looked and said, oh, that really wasn't a number 2, that was a number 3. That really wasn't select structural, that was number 1, because the graders missed. When you're visually grading, you make mistakes every so often. Actually, the standard allows them to be wrong 5% of the time. Or that's a reason why you might go with non-destructively tested lumber to automate that process and get rid of a couple bad actors. All right. So the base, it's either the mean value or this L5. That if we've got a normal distribution, that L5 is it 1.9 6 standard deviations below the mean. Let's look at this next factor, and this is what is going to be motivating. This is a pretty big knockdown, and that's what's called duration of load. So let's take a look at this. This curve shows up in many, many places. It shows up in your national design specs. It shows up in ASTM standards. This was developed again back in the 1930s originally, and it's often referred to as the Madison curve because the work was done at the Forest Products Laboratory in Madison, Wisconsin. Really important curve. So let's take a look at this. On the x-axis is duration of load. So yeah, you took design of structures, right, Elliot? So you've seen this before. You've done some design. Anybody else taken a wood design course? Long ago? Okay. This turns out, this is a huge, huge, huge deal. Edwin Nagy teaches, it's a 500 level course, I think, design of wood structures. It's taught in civil engineering here, if you're interested. You'll see this all the time. Anyway, on the x-axis, we call duration of maximum load. Let me get out of here, actually, and just kind of zoom. Let's zoom this up. Open. Okay. It is hot. So this is figure X1.1 from ASTM D2555. X-axis, we have time, duration of maximum load. 1 second, 1 minute, 1 hour, 1 day, 1 month, 1 year, 10 years, 50 years. So we've got kind of a logarithmic scale to some extent going on here. And on the vertical axis is ratio of, it says ratio of strength to that for load duration of standard strength test in percent. Here's the important part, 100. When you test lumber, when you test your pieces of wood or your composite materials and you follow that ASTM test, they say test at a certain speed. Or they'll say test such that failure will occur in 5 to 10 minutes or 3 to 10 minutes. So this is, I believe, 10 minutes is considered the duration of a standard test when you test the material in the laboratory. Failure occurs in 10 minutes. We measure the strength, 100 psi, well, 10,000 psi, 8,000 psi. So what the Madison curve says is I got this piece of wood. Let's say I could create, I'm using additive manufacturing, and I am printing 2 identical pieces. 2 identical pieces of wood or pseudo wood things. Yeah, we could do this now. We could do this with additive manufacturing, kind of surrogate stuff. All right, I got 2 identical pieces. I take the first one, I test it, and it breaks at 8,000 pounds in 10 minutes. We'll call that's our baseline, or 100%. If instead of it failing in 10 minutes, I tested it faster and caused it to fail in 1 minute, it says it's not going to fail in, it's going to fail at a 5% higher value because we're at 105. 5% stronger if I break it in 1 minute instead of 10 minutes. Or if I take an hour, it drops from 100% down to 91%. So if I took an hour, it will drop by 9%. This happens over and over. We've observed it. That's why the standards say you must cause it to fail within a certain time frame. because what you'd want to do is, oh, if you're just reporting the values, I'm going to cause it to break in a minute. I'm going to cause it to break in 40 seconds. You're going to get bigger numbers. And you compare it with somebody that's, oh, I'm paid by the hour. I'm going to go really slow and I'm going to break one piece an hour. Well, now you got 20–30% difference between the answers, even though they were the same material, because the rate at which you applied your load. An hour, a day, a month, a year, 10 years. And I've got 10 years circled. This will go up to 500. I think now I can play this. I got that point. Okay, the 10 years. 0.625 is that value. So what that means is when you look up the design values for wood to build a structure, it is assuming that a load will be on there for 10 years. This building's going to be around a long time. So that is your base design load, except for E and FC perp. It's assumed that the load, those values have been adjusted to a 10-year load duration. Why? Wood is viscoelastic. This is characteristic of a viscoelastic material. That's a really big impact, that low duration behavior. So any viscoelastic material is going to exhibit this type of dependence. So a polymeric composite will also. The Madison curve may not apply to polypropylene wood. It may have a different shape, a different slope, but there will be a curve such as that. This is the result of lots of work by lots of people all over the world. There are other curves. The British use a different curve. Well, now it's the EU uses the Canadians use a slightly different curve. But they're not that different, but there are different curves out there. We use the Madison curve. Obviously, this is important. Now let's move on to from a structure standpoint. Okay, I look up that value in the design handbook. I'm designing my building. It says it's this strong, and I can back my calculations and say that means it could take this kind of load, and it wouldn't break if that load was there for 10 years. But there are cases where we have, well, here, live loads that is our base, our 10-year duration. A live load is a term we use for designing a building, the people that come in it. So like a home is going to be designed for a 40 pounds per square foot live load. Over the life of the structure, it's kind of interesting. If we go to, can I do it? I'm going to lose this if I go to the board. Can I sketch this somehow? Should be able to. Let's bring up Mathematica. I think I can just bring up my drawing tools there, right? Graphics, drawing tools. Oh, and I need a new graph. Okay, now let's do this. All right. So let's say I've got on this axis time, and on let's call this vertical axis load. And we'll call the horizontal axis time. Now let's say I'm designing and it's the design codes that are provided by the government that says if you build a house, you shall design and expect that there is a 40 pound per square foot live load. How they get that, that's a whole nother story, but you are required legally to design for that condition. And if now you go into a house and okay, there's nobody here for a while, then you come and you walk in the room and then there's a load here and things going on, then your friend comes over, and then it goes back down, you go to work, you go in the other room, you got a party, comes back down, nothing's happening, you know, it's not constant over time. But what they've rationalized is that if you go over the life of a structure, which is assumed to be 100 years, and you add up all of these events and add them together, they'll add up to be 10 years over the life of a structure. So 10% of the time, there's actually somebody in the room. So that's 10-year, 0.625, viscoelastic. Okay. So a structure exhibits other types of loads. You have what we call the dead load, and dead load is the weight of the structure itself. In the US, we define that as being 100 years. Say a building won't be around more than 100 years. So there's cases where that's not the case, but that's what we define as a permanent condition, a dead load, and that is the weight of the building itself. There are other types of loads, snow loads, snow and snow loads, wind load, no. Yeah, snow loads and wind loads are a 2-month duration. There's what's called that should be wind. Again, snow could be constant for 2 months, depending on where you're at. Wind loads are going to, again, aggregate over time the maximum loads of wind, because you're going to have wind all the time a little bit. It's pushing against the building. But again, these maximum values, they say, are going to aggregate to be that value for a total of 2 months. Roof live loads, that is the weight during construction, which may be the shingles that go on the roof of the house while you're shingling. Other things like that. And earthquake loads, really important. They're considered, that load, which is from the shaking of the ground, is considered to last a minute. So in the design guidelines, the values actually are that you look up are for 10-year duration, but you follow the same curve. If you go to 1 minute duration, we're going from 0.625 to 105, which is almost a doubling of strength. So when you say what the earthquake load is, you take the design values from the book and almost double them because of that. And you have different load combinations and things. It's a long process we're not going to go into. But this is, for designing in wood structures, this is uber important. Why? Because wood's a viscoelastic material.
stuffs that we have inside the house, like, do they consider as live load? Or
Furniture would be live load.
Does that curve kind of explain why hurricanes are so destructive? Because it's a fairly large load over like maybe a day or two.
Well, I mean, the loads are more than the engineers designed for. They know about this curve. One of the problems with hurricanes, a lot of failures, is the when you have a. Oh, I want to do this now. I have to bring up Mathematica and do my sketches again. If we look at a house, let's just pull this down. Can you do this in MATLAB? No? All right, just checking. If we look at a house, and we have wind coming in. Let's try this. Let's say it's this direction like that, okay? Because of aerodynamics or fluid dynamics kind of things, it turns out that you end up with, on the back side, forces pulling away like that. So it tries to pull the roof off the house. This now gets controlled by the connectors, pulling the nails off out of the wood. And the big, I think that was what, Hurricane Andrew 20 years ago, some 15 years ago, down in Florida, which had a couple $1 billion worth of damage. Then they go in. Look at all these rotten, these bad wood houses that got destroyed by the hurricane. They lost roofing because of poor construction practices. There weren't the right number of nails, or there weren't as many nails as there should be, or the nails were shot in, but they didn't go into the wood underneath it. So it was a connector failure because of not following the design guidelines. That get pulled off, then it rains 2 inches, 8 inches of rain, which ruins the house because it's soaked with water. That turned out to be much more of the issue rather than a failure of the wood or the material itself because of the high winds. Now that can happen, but this is more often the case. And this brings in this issue, which we don't talk in this course about, is connectors. In a structure, that's everything. A lot of times failure will occur there. Okay. I think that's
makes sense. If you're doing demo, that's where you start.
Yeah, it's the easy part. So we got that value of 0.625, and we've got this load duration behavior, why it's a viscoelastic material. So let's talk about what is viscoelasticity. When I was in graduate school, I took a 3-credit course just on viscoelasticity. I mean, this is a big subject in and of itself. We're just scratching the surface of it. But we can define a viscoelastic material as something that exhibits elastic and viscous or fluid behavior. So it has a character of both. We see when we deal with wood or wood composites, we see this viscoelastic behavior come up in many different situations. One being when we talk about the creep of a material. That is its deflection over time. We see it come up when we talk about stress relaxation in a material, which is just a different boundary condition for the same differential equation. When we start to talk about that, it's just a boundary condition situation. We'll define these in more detail later. But there's also this effect of strain rate. And we talked about that briefly, and it's saying, oh, if I test it faster, it's going to be stronger. If I test it slower, it's going to be weaker. So the faster you test it, we'd say it has a higher strain rate. So what is creep? Creep refers to, and you'll be seeing a lot of these double sets of curves. We've got the axis of time, vertical axis is load, vertical axis is deflection. When we normally break things, right, we plot load versus deflection. And then each thing is at a different point in time. For creep, load versus time, deflection versus time, and let's say at what we apply is, this would be called a, at some point in time we put a load on it, the load is constant, we take the load off. This would be the standard loading situation to do a creep test. The deflection of the material might look like something like this. Creep refers to this increasing deflection over time under constant load. Creep is the increase in deflection over time in response to a constant load. There's been at least one or two of you, your papers are about visco. So yours is on viscoelastic? Okay. Anybody else going to be working with this at all? Not so much. This comes into play, anybody doing dynamic mechanical analysis? DMA? Going to be using a DMA? A little bit of DMA. This becomes very important in DMA depending on your load conditions. Got to bring that up. So for example, if you're doing a test, if you're doing a vibrate, it's important. We'll get to it later. Okay. But you can have, there's what's called offset loads and things will creep over time, and so it becomes important. Let's look at this term stress relaxation. So again, we have these two same set of curves, deflection versus time and load versus time. Now note, now I'm going to have deflection is going to be controlling, and load is in essence going to be the response. So let's say now I apply a certain deflection, keep it constant over time, and then take away the deflection. Physically, here we could see, okay, I put a weight on something, I take the weight off. Or I program the testing machine to quickly go to a certain position, a certain force. I have books on my bookshelf. I put them there at the beginning of the semester. They sit there. They don't get used all semester. And then at the end of the semester, or when you graduate, you take them off. Deflection. What might be conditions that will create a constant deflection over time? Anybody a woodworker?
Clamping something, yeah, clamping something in place.
Clamping something in place. So you're gluing something together, and you got clamps, and you clamp it up, and you Say, okay, that's good, and you come back the next day and you take the clamps off and the clamps fall off. Or you are pressing something and you're in position control in the press, and you say, you put your material in the press, it's 4 inches thick, you say go to a half an inch. I'm going to press to a half inch and stay there. And then when I'm done pressing, after things are cured, open up. So a position control press. So that's where this stuff really comes into play, is pressing dynamics of hot pressing of composites. Viscoelasticity is critical to understand what happens during the pressing process. In stress relaxation, the load required to maintain that constant deflection decreases over time. So my boundary condition is I am causing a certain deflection. I'm not allowing that deflection to change. The force required to maintain that deflection will decrease. So on a press, if it's a position controlled press and you can record hydraulic pressure, you'll actually see the required hydraulic force drop over time. Or that thing where you're using hand clamps to glue pieces of wood, and the next morning you unglue it and or you unclamp it and it just falls off. There's been less force to do that. When you make glue lam beams, I've seen it in plants. They'll come in if they're using air guns and tightening things up using bolts and bolts and nuts. They'll tighten everything up, then they'll come back again in a half hour, an hour, and retighten everything up again because of that stress relaxation that's occurring. They're not getting enough pressure. The stress, here we talk about load, but you would just divide by area in a uniaxial case to talk about stress. Now the stress would be too low to get a good bond joint. You have to deflect it more to increase your stress to the proper level needed for a good bond joint. If we're gluing pine, what's the kind of compressive stress we often have for gluing wood, solid wood together? Ballpark. In PSI, if you know it in PSI, I don't know it in pascals.
Compression for like pressing it?
Well, for gluing solid wood, like a glue lam beam, or if you're pressing wood for to make a butcher block table or something like that. Any idea? It's going to be around 100 pounds per square inch, maybe 140, maybe 90. Lower density species, it's got to be lower. Higher density species, it's higher. But around 100 psi. Can we convert that to pascals? Anybody? You know that? 3 point. I don't know it off the top of my head. I know psi doesn't mean much to you. So convert it to your pascals, and so it's about 100. So strain rate. This we talked about. If we test some, so here our curve is
0.689 megapascals and 100 psi.
okay. So less than a megapascal when you're gluing wood together. If you go too much, you're not going to get a good bond. You're going to crush the wood. You're going to squeeze out too much of the glue. Depends on the type of adhesive you're using, but okay. So here, if we look at strain rate, now let's have load and deflection on the same curve. If we increase the load and measure the deflection slowly, we would get a curve. If we did our test faster, we would get a steeper curve. In this case, we'd have a higher E, and it would be stronger. And if we test even faster, it would be stronger and a higher E, because we've got a steeper slope. How are we doing time-wise?
15, 20.
Okay, so I got another 15 minutes. All right. So that's called strain rate dependence. The faster we test it, the higher the strain rate. That is the derivative of deflection with respect to time. This is creep. This is stress relaxation. you can have the same underlying mathematics, and this is just different boundary conditions. So there are two, if now we want to get into the math and describe models that we can use to predict viscoelastic behavior of materials. There's a couple different ways to do this. This is the classical approach. Rheological models where we'll use what are called springs and dashpots. These are analogous to resistors and capacitors and electric circuits. And you end up with differential equations or a series of coupled differential equations to describe the behavior. And it is the exact same thing that an electrical engineer would use to describe a circuit. Same mathematics, different interpretation of what the components are. A spring, we think a spring, an electrical engineer says that's a resistor. But the math is going to end up being the same. And we're going to talk about voltage, they talk about voltage, we would talk about deflection. So you get these analogies. So this is all we've talked about this year, this semester, are springs, spring constant E's. Now we said there's E1, E2, and E3 depending on the direction, and if for some other direction its value is E between, but we said there's just an E. Stress over strain equals E, it's a constant. So if we apply a load P to a spring, that spring is going to stretch. And the amount, and it's going to stretch by a certain value, a certain deflection value, delta. I don't know if I could create these, I think I could create these animations in Mathematica, but this is a better tool for that, a little easier. Now let's look at these sets of curves. We're going to again be seeing this load versus time and deflection versus time. So in this case, load time, deflection time, at some time I apply that load P. Load goes up, we'll say it's instantaneous. If you zoom in on it, it's going to have a slight angle. A spring, we says, deflects instantaneously. And that is related to the spring constant. In physics, that would be K, is often used as the spring constant. If I keep the load constant over time, deflection will not change. It's at equilibrium. And then if I remove the load, the deflection will go away. So a spring element deflection is instantaneous and recovers when we remove the load. Just tracks it. So we're comfortable with that. That's what we're used to. So we would say E is a constant. Let's see. Just because. So in Mathematica, we would say E would be equal to some constant plus 0 times time, t. That would be one way to represent it. All right, we apply a load, it elongates a certain amount of deflection, load constant, no change in load, no change in deflection, remove, remove. Or your boundary condition could be deflection, and you would have a load required to create that deflection, and same thing's going to look like. Okay, and then that deflection is delta, is that deflection. So the other base element used to describe, to build up these rheological models of viscoelastic materials is called the dashpot. This refers to a viscous material and when we apply a load, I'm showing things in tension. You could have the same kind of thing in compression. What will happen is that will pull apart, but it's not going to happen at once. It's going to happen slowly. All right? So we have a dashpot, we apply a load. Okay. So examples would be, well, it's drawn this way. If you had a can full of water, and then you put a plate in the water with a rod attached to it, and you try and pull it up real fast, well, if you're strong enough, all the water comes out of the top of it, right? But if you pull it up, but it doesn't want to come up right away. But if you pull it up slowly, you can pull it up to the top. And this is what we use to describe a Newtonian fluid. If the viscosity, and we'll get to differential equations later, but if the viscosity is a constant as we related to strain rate, it's a Newtonian fluid. A dashpot, the deflection is a function of time. It's not a constant. So delta is a function of time. So let's put our nice two little curves up there again. Load versus time and deflection versus time. And let's see how a dashpot. In this case, our boundary condition is going to be constant load. So anybody want to predict if I draw this curve, constant load, a jump in load, constant load, drop the load, what the deflection curve is going to look like? What do you think?
Like a live load, maybe.
It will go up and back down.
Okay, go up and go back down. Going to be steady. The load, the deflection.
But it goes up at first, but then it stays there.
Then it's going to be steady. So initially, when we apply a load, there is no deflection. As that load is constant, our deflection increases in a linear fashion for a Newtonian fluid. Or if it behaves this way, we call it a Newtonian fluid. Then when we remove the load, the deflection doesn't change. If you were in space, outer space, and no gravity, but if you had the rod in a can on Earth, it's going to go back down because you're applying a force in the other direction. So that deflection is a function of time. In this case, it's a linear function. So deflection continuously increases under load and does not recover upon the removal of load. What we're going to do, we won't get to it today. Probably it'll take us through all next week to get through this. We'll show a couple more models. We won't get through them today, but we'll describe the differential equation, which models these, and then we can, for example, do a DMA test and say not a constant load or a constant deflection, but we can define a sine load as a boundary, as what we call the forcing function to the differential equation, and see what that phase shift is, which is what you measure in a DMA. So DMAs assume that you have I think it's the Maxwell. The spring and dash pod in series is in the DMA software. That's what they assume you are testing. All their answers are assuming that. And so that's not true. This is the Maxwell fluid, which is a spring and a dash pod in series. So what we want to do is add the behavior of those two in series. We know how each behaves singly. Let's put them together and figure out what that behavior is going to be like. So I have my spring and my dash pot. I apply, and I've applied the load that at time 0, that spring instantaneously moves. The dash pot, nothing happens. Over time, this thing will change. So the total deflection is the deflection of the dash pot, which is a function of time, and the deflection of the spring, which is a constant value. So once again, load versus time, deflection versus time. We'll do the same boundary condition, constant load. What's going to be the initial deflection? Spring constant, it'll be K. So there we go. Now, then I'll have a line. So the initial deflection is delta, which is the spring. For a constant load, I'm going to get that straight line, which is the behavior of the dash pod. This distance from here to here is going to be, I didn't want to do that. All right. All right, you saw it, but let's go through it again. I thought I had something else. Boom. Deflection. That goes up. What happens when we take off the load?
So the spring goes back.
The spring goes back, and then it stays. So the amount that this drops is delta, which is the same as the initial spring extension. And this permanent deflection is the same. I think I've got it. Well, it's the same. It's this distance from here to here is the same as this distance from here to here. So deflection has an elastic and a viscous component. Therefore, it's a viscoelastic behavior. The spring itself is elastic. If we describe the response of a material by a dash pod only, that's what you do in fluid dynamics. That's a Newtonian fluid. And if you combine the two, you have a viscoelastic material. Mechanics is easier, static is easier because you don't have time. If you get in, whereas fluid mechanics is considered harder because you've got that rate effect. Okay, that's all we have. Speaking of time, that's all we have time for today. We will follow this up on Tuesday. I'll record this part of the lecture and post it, so you'll have the animations, okay? I can have a good weekend.